Okay, welcome back. We are in a bunch of torque problems right now. And let's see if we can't get just a little further in. Where we're at right now is we're in these problems where the sum of all the torques are equal to 0. And this is a classic, very classic problem where we've got a uniform beam of some kind that's been pinned to the wall. There's a guy standing on it, and there's a cable attached out here to the end of it. Now, I guess I don't mind it for the sake of learning, but I hope that, when you get to the harder problems, they do not include any form of broken down free body diagrams, because the biggest part of torque problems for most people is learning how to do these diagrams. I'm going to put my hand over that and pretend like it's not even there. And what I'm going to do is go ahead and see if I can't get me another sheet of paper, and I'm going to see if I can't draw the picture in this question, or I can't draw a free body diagram for it, because that's what's the most important. Well, we start looking at the picture. Now I'm trying to get up here in this corner, and it says right off the bat, uniform horizontal 300 Newton beam. Now that uniform means I'm going to go right to the middle, and I'm going to draw force straight down of 300 newtons. So there's what the uniform is telling me in this question. Now, it also says the beam is 5 meters long. I need to get that. There's a cable out on this end, and this cable, I'm going to put me a dot where that cable is to represent, that's where the force is acting. And that cable is, well, I got a little crooked on my line. There's a cable that says it's at an angle of 53 degrees, and it doesn't tell me what, but it says that there is a tension in that cable out here. It also says that there's a person standing here against the wall. It says this person is standing here. I'm going to put a dot there to represent that person. And I'm going to draw their force straight down. It says that they weigh 600 Newton. Hey, make sure if the problem gives you kilograms that you times it by 9.8. I've seen people miss these questions because of that. This is where people now kind of butcher this question. Obviously, there has to be some force. This guy's standing here. If this pin is not holding him up, he would just come right down. So we know I'm going to put a dot right here in this corner, and I'm going to draw a force straight up. And I'm going to call that the reaction force Y. This is where people miss this. But this needs to be automatic. When you see this problem, this picture, you need to go to this pivot point on the wall, and you need to put an RY. And then also, here's the thing. If you look at this problem, there's got to be one more force. Because you see ups and you see downs. This tension, though, is angled left, which means there's got to be something to the right. And right now, there's nothing to the right in this question. So I'm going to come back, and I'm going to put right here. I'm going to put me an arrow right here. Bam! I hope it shows up on this video. And I'm going to call that Rx. So that's called the reaction force in the X dimension on here. Now, here's what happens. Everybody gets in these problems. They're like, oh, we're doing torques, we're doing torques, we're doing torques. Let's do torques. The thing is, any of these hard equilibrium problems, you not only have to do torques, you got to also do sum of the forces. So if you thought, I'm done with sum of the forces, I'm sorry, you're wrong. You've still got to keep doing this. So let's do that. Sum of the forces X, sum of the forces Y. Notice I'm doing this before I haven't even picked a pivot point or anything yet. I'm doing a sum of the forces. As soon as my picture is done, I start doing a sum of the forces. So I look for anything pointing to the right. Well, that's my Rx. And now I come back, anything pointing left. Well, I'm on minus T cosine 53. If you do not know how to do a sum of the forces, well, you need to go back to chapter 4, unit 4, and learn that. Now, anything pointing up. Well, I've got an RY. I've also got this T that's pointing up. So I'm going to plus T sine of 53. Now going down, I've got a minus 600 and minus a 300. I'm going to set everything equal to 0. You see, this is called the first condition of equilibrium. The first condition of equilibrium says that your sum of forces x and y's both have to be equal to 0. The second condition of equilibrium is that, wow, I can barely talk. The second condition, though, is that the sum of all your torques. Well, okay, now I'm ready. Now I'm actually going to do this sum of the torques part. Well, now we need to actually do a little pivot point picking and all that kind of stuff, and we need to get some measurements down. It says in this question that the beam is, from one end to the other, the beam is 5 meters long. Well, let's start picking a pivot point. Well, hold on, one more thing. It says that the guy is 1.5 meters from the wall, so I'm going to put a 1.5 where the guy is. And I'm kind of going to go ahead and do something. I'm going to go ahead and pick the wall to be my pivot point. I just do that a lot. So I'm going to go through. He's 1.5 from the wall. It's uniform and 5 meters long. That means that this should be at 2.5 and that this should be at 3. Why did I write 3? This would be 5 out here. So I've got all my R's, and I'm ready to work this problem. I just need to know clockwise and counterclockwise. Well, by this point, you should be getting a little better at it. This 600 Newton force, notice how it's pushing down. So clockwise, 300 clockwise. And then this T, kick my camera, is a counterclockwise. You push up and then angle, notice how it's trying to move. So I'm going to add up my clockwise, now subtract my counterclockwise. Well, let's do this. We've got a 600 times 1.5. Now I'm going to add in the other clockwise. This 300 is also clockwise. So plus 300 times 2.5. I don't have any angles. That's why there's no signs for those. Now I'm going to subtract my counterclockwise torque. That's this tension. So minus T sine of 53. And there's where people screw up. They forget the R. Remember, it's an F and an R. So here's my F sine theta, and my R is 5. And the second condition of equilibrium says that the sum of all these torques should be equal to 0. Now I can come back in, I can start getting some answers in this question. 600 times 1.5. Well, there's 900, and I could have done that in my head. I feel kind of silly now. Well, here, I'll prove it on the next one. 2 times 300 is 600, half, so it'll be 750. And this is minus sine of 53 times 5 is 3.99. So that's basically 4t equals 0. So now we've got 650 equals 4t. 1650 divided by 4 is 412.5. 412.5. So there. The tension in the wire is 412.5 newtons. Now, if you want to go back and get Rx now and Ry, all you got to do is plug it back in. So if I want Rx, let's take this equation and pull it on down here. Rx would be equal to T 412.5 cosine of 53. So 412.5 cosine, oops, I hit tangent, cosine 53. If you got 248, then good, you're in the money. So that one's 248. If I want sum of the forces Y, I can get sum of the forces Y, or excuse me, if I want Ry, I can get it right here. I don't have to do a bunch of torque equations over and over. So I can go back to here, and this would be Ry plus, I've got 412 sine 53 minus, what have I got here? Minus 600 minus 300, so minus 900. All that equals 0. 412 sine 53 minus 900. So this is Ry equals 571 newtons. And now I can go back through, and I've got every single possible answer that this question could want at this point. Alright, if you're good so far, and again, the most important thing is learn how to draw this picture. You're going to see those questions over and over. One more time, real quick. How do we do that problem? Draw your beam. It's going to be the question where there's something up on the wall. They're very generic. They always look like this. When you go to draw your beam, bam, bam, chew. Draw your beam. Usually you'll have some weight dead in the center. There's usually a tension at some angle. And then the big thing that everybody messes up, over here you will have an Ry and an Rx at this point. And that's where everybody kind of gets messed up in this question. Alright, I'm going to do a second video on nothing but ladders. So if you want to see how to work a ladder question, which is a very common question, propped up against a wall, that'll be the next video to follow this one. Thank you very much.